Hello everyone and welcome back. My name is Mr. Cobalt, and in this video we're going to go over acid strength and molecular structure. And in this video there's two kinds of acids we want to deal with. There's the binary acids and then there's oxyacids. So in this video I'm going to focus on the binary acids, and then in my next video I'll talk about oxyacids. So what is the connection between molecular strength and acid strength, or molecular structure and acid strength? So there's two questions that come up. Is that why are some hydrogen-containing molecules, why do they act as acids and some don't? Or why are some acids strong and others weak? And so we're going to answer those questions with respect to both binary acids and oxyacids. So let's talk about binary acids. So the thing we're thinking of is, with regard to these questions, is if we have a molecule like HF and we have another molecule like CH4 methane, then the question is, why is this one acidic but this one is not? Why does this one not give off hydrogens but this one does? And so to begin, we're going to talk about binary acids. And binary acids are the acids that contain hydrogen and one other element. So hence the word binary. Bi meaning two, two elements. One of those elements is hydrogen and the other is some other element. So the generic form would be HX. So there are two factors that are going to affect the ease of donating the H to water. So one is bond polarity and the other is bond strength. So let's talk about bond polarity for a moment. So if we go back to what we learned before in an earlier video, the polarity of the bond is indicated here using our arrow. And so we have a dipole moment in the bond, in the molecule. And so here, this happens when you have a difference in electronegativity that is fairly large. So here, the arrow points to the more electronegative atom. The more electronegative atom is the one that's going to pull the electrons in the bond more towards it. And so the electrons are going to spend more time around that atom. So here, that's going to give this X a partial negative charge. And that's going to give the hydrogen a partial positive charge. And the partial positive charge is going to make the hydrogen more likely to come off because we're trying to form H plus ions. And so if the hydrogen already has a partial positive charge, that's going to make it easier for it to be donated. So again, especially to water, because water has those unpaired electrons, those lone pair electrons, which are negative, and that's going to have attraction to the H plus. So it's going to make it easier to transfer the electron to transfer the hydrogen to water. So that's part of what the importance of bond polarity does. And that's going to be based on the difference in electronegativity between the hydrogen atom and the other element that it's bonded to. So we can see here as an example, right? So here we have H and lithium, here we have hydrogen and carbon, and here we have hydrogen and fluorine. And so here, the lithium is not as electronegative as the hydrogen. So here, the hydrogen is more electronegative, so much so that this ends up being an ionic substance. So HLi, the hydride of lithium, is going to be an ionic substance with the hydrogen having the negative charge. So this is not going to be acidic. Okay. Here with the HC bond, your carbon hydrogen bond here, this is where the electronegativities between the carbon and hydrogen are pretty much the same. They're very close to each other. So this ends up being a non-polar bond. So there's really no partial negative, partial positive side. So this is not going to be acidic. But then with HF, fluorine is highly electronegative compared to hydrogen. It's going to want to attract those electrons towards it. That's going to definitely give this side a partial negative, so on the fluorine, and a partial positive on the hydrogen, and so therefore hydrogen is going to be easily coming off, and so therefore your HF is acidic. And so that's how bond polarity affects acidity. What about bond strength? So we're talking about bond strength. So here we have the three acids, and we have HF, hydrofluoric acid, hydrochloric acid, and hydrobromic acid. And here we have the bond energies for each of these. And you can see that the bond energy for HF is larger than the other two. So 565 kilojoules per mole for HF bond. For an HCl bond, it's 431. And then for a HBr bond, it's 364. So these two have a much weaker bond compared to that of HF. And so it makes sense that if you have a very strong bond between the hydrogen and the other element, it's going to be harder to get that hydrogen off, and it's therefore the weaker the acid will be. So here we see the bond strength or the bond energy in this bond is much higher. Therefore, it takes a lot more energy to break that bond, which means it's going to be less likely for the hydrogen to come off. Whereas for these two, the bond energy is relatively small, so it's much easier to remove these hydrogens. So it makes sense that HCl and HBr are strong acids, because meaning that they dissociate completely in water, because removing the hydrogen or transferring the hydrogen is much easier with these bond strengths, because the bond energies are low, the bond strength is low, compared to HF where the bond strength is pretty high. So it's harder to get this hydrogen off, and therefore this is a weak acid. Okay, so we can kind of put this together in a table. So if you look at the hydrides of your group 6 elements and your group 7 elements, and we look at those compounds, and we look at how in the periodic table the trend of electronegativity increases this way. And so you could see that as the electronegativity increases this way with the element in the table, so fluorine has a higher electronegativity than oxygen, then you can see that the acidity of the substance increases this way as well. So here fluorine has a higher electronegativity. It's pulling on those electrons more, therefore giving hydrogen more of a partial positive charge, compared to oxygen, which isn't as electronegative. So the partial positive charge on hydrogen is not going to be as great. So it's not going to be as acidic as HF. And the same thing with H2S and HCl. So again, electronegativity is increasing this way, therefore the acidity is also increasing this way. So HCl is a strong acid, H2S is not. Okay, so what about bond strength? So as you go down a group, the atoms are getting bigger. So sulfur is bigger than oxygen, selenium is bigger than sulfur, and so on. So the atoms are getting bigger, so the distance apart is increasing, so therefore the bond strength between those atoms is going to be lower. So as the bond strength decreases, it's going to be easier to remove that hydrogen, and so you would expect the increase in acidity. So as you go down the group, the hydride becomes more acidic. Same thing with this group here. So here you can kind of see the patterns based on bond polarity, which is based on difference in electronegativity, and bond strength. I hope this video was helpful. In my next video, I will go over oxyacids, and we'll talk about acid strength for oxyacids. If you enjoyed this video and you got something out of it, and this cleared a lot for you, please make sure you hit that like button, subscribe to my channel. Make sure you hit that notification bell so you'll be notified by other videos I put out. And put a comment in the comment section below. Let me know what you think, and ask me any questions. Thanks for joining me. Have a great day.